Hello everyone, welcome to chapter 29, reading shop drawings. The next chapter, chapter 30, is going to be breaking down the welding symbols and kind of going through the individual pieces of the weld symbol versus welding symbol. Two different things, we'll discuss that in chapter 30. 29 is a fairly quick chapter, but it kind of gives you a broad overview of what we're looking at. I think it's essential to do it. To go through this chapter before we go into chapter 30 as well. Okay? Alright. So, reading shop drawings to start with, objectives. You can read through those on your own. By the end of this chapter, we're going to be able to read, the beginning stages of various drawings. There's still a lot of things out there that we want to cover by far. But this is just kind of getting the conversation started. We have to start somewhere. And that's why we are going through this chapter to begin with. Okay, the drawings and shop sketches. They're sign language of industry. They transmit ideas from design to finished product. It's a universal language of craftspeople all over the world. Workers read drawings to produce identical matters or parts, no matter where they are. There is a ton of information that you can get off of a very simple little picture sometimes. And then there's times as well that you're not going to get the whole picture. You're going to be frustrated, there might be a part left out, or you may have to look at it and deduct 6 things from it in order to figure out the one portion. So for example, if we have a circle, 3-bolt pattern, or a 3-hole bolt pattern laid out on an even spread, divided by 360, so we know they're 120 degrees off. We may try to find where it's at right angle, either 0 or 90, and that's our start point. And from there we'll have to make the calculations and do the mathematical formula to kind of figure out, okay, what angle is this at, what angle is that at, relative to this. A lot of things can be taken away from the drawing. It's just we have to learn to slow down, work on one part at a time, and not get overwhelmed by the entire picture, okay? And that's what we're mainly going to focus on, is just slowly taking it one piece at a time. You have to build a puzzle one piece at a time. You don't dump it out and they all fall into place. We have to learn, do one piece at a time, and we'll slowly build this thing the correct way that it needs to be done, all right? Purpose, we kind of just talked about it. You can relay a lot of information. You'll be able to, plan accordingly. Make sure you have the right parts before you go into the field. A lot of times, if you're reading prints, you're looking at this. You may do what we call a takeoff. So you might be going to the parts house to get the material before you go to the job site. So you want to look at the print, figure out, okay, 90-degree fittings, I need 1, 2, 3, 4, 5, 6. I'm going to get one more as a spare, as a backup. 45s this, T's, 1, 2, 3, 4, so forth. Roughly, 4 foot here, 3 foot 6 here. This is the total amount of pipe I'll need. So in this case, I'm going to need to be able to remember to bring enough equipment to cut the pipe, prep it, materialize it, to be able to get it ready to fabricate back together, okay? All right. There's several different types of drawings. There's detailed, there's assembly showing how they all go together. And then sometimes you can have assembly drawings with detailed views in between them, so forth. Originally done manually or with computer-aided drafting and design. Sometimes you're going to get out there and you're just going to get a plain old shop print. Or you may have to create your own just to make sure that it goes right, or pull your material supplies real quick. Say, okay, I'm going to come down here, go here and there. Rough estimate of material. I can do that in 20 feet, 4 90-degree fittings, but I'm going to need a drip leg T here. I need a valve here, check valve there, and you're going to draw yourself an isometric shop view a lot of times before you go into the field or before you go to the job. If you don't have a print already, it's important to know and use to keep things straight in your mind as well. All right. So if you're following along in the book, we're on page 972, chapter 29. Let's go back to the types of drawings. It's on page 973. Let's left-hand column, bottom section, bottom paragraph, right above the sentence, right above the bolded items, says that welders should learn to read and interpret plans for the following reasons. A journeyman welder can interpret plans, always in demand and on any job, and is likely to be given responsibility. That's the main thing that I really wanted to hit. And believe it or not, you cannot imagine how many people out there have a hard time being able to interpret drawings, break them down, and so forth. When I worked at the mine, there were 7 welders, and when we would get a critical piece of equipment in, so like a ROPS, which is a rollover protection system. So basically, we worked on large mining equipment, large Caterpillar equipment. So this is a Caterpillar print that's coming to us, and this can be in it doesn't have to be on mining equipment. It can be road construction. It can be in race cars. And what it is it's a structure for the inside, so that if you were to roll over, it's designed to help protect the driver from being crushed. Okay, it's to save their life. So you'll get this, and it has to be followed to the print exactly. Otherwise, it will void the warranty of the complete truck. There's usually a tremendous amount of oversight in a QA or an engineer that's got to come behind the welder and spec and make sure that it's welded exactly like that. The rest of the machine you may not have to do that at all. But on that rollover protection, there's a huge liability within corporations across the country and the world that say that has to be drawn within spec, it needs to be checked, or they won't even let you operate, okay? Now, out of those 7 welders, I was one of the only one of the 2 that could read a print. And we were on exact opposite shifts. So, luckily, there was always one of us there, me and another gentleman, that were able to read the prints. When he switched, it put a big dent in production, because there was a week-long period there to where the welders didn't understand quite what the prints meant and how to interpret them. So they actually had us put on a class and explain to the rest of the welders, what does this mean? What does this welding symbol mean? So they could do the same thing. Some of them have been welding for over 30 years. They were phenomenal welders, absolutely great welders, fabricators, everything. They just had a hard time reading the technical drawings and being able to interpret them to the correct level and expertise that needed to be done. Okay, feel free to read through the rest of those bolded items. Let's go to, we're on page 973, let's flip over to page 974. There's methods of print drawings. Okay. Now, this is kind of, we're going to have to bounce back and forth a little bit here. So what I want you to do is I want you to, let me see if it's on the print here. They're not breaking down the measurement size real quick. So on page 974, chapter 29, figures 29.2 and 29.3, they show standard drawing sizes in inches. An E size would be the largest, while the A size would be the smallest. So an A is an 8.5 by 11 for the most part. So that's a normal typewriter, or a normal size sheet that we're used to. Okay. E, you can see it would be a much bigger piece, like a traditional blueprint for a home or a building that you might see. And then in 29.3, it shows you the standard drawing sizes and SI units. These sizes will be encountered when working on prints coming from outside the U.S. The AO size will be the largest, while the A4 size would be the smallest. These letter number combination codes may appear on the specification, so you must have an idea how large the print will be. And it's important that you understand both, not just in the traditional English version, but but in the metric, the SI units as well. Okay. One of the things that I think is rather unique nowadays is that the electronic and digital age is prominent in everything, and they now are selling equipment without the operator's manual. You can go online, type in this model serial number, and you can download it so you can see it, but it's saving them paper to not print it and send it with the equipment. I don't know that it's in automobiles, but in some smaller equipment I noticed that we are starting to get more and more. It says refer to a website if you need help with the operator's manual and so forth. So some of the prints we're going to see, you're going to see a digital print. They may send you the file instead of sending you an actual set of prints. So you're going to need to kind of maneuver around, quite possibly with the computer and technology some today as well, on top of reading traditional shop drawings or prints. Okay. They should be handled carefully in the field. Avoid thumbprints by handling by the thumb room space left along the edge. And this goes for, very, very typical, do not mark on the drawing. I've done it a lot of times. I completely space about it. I'll get my pencil down and I'll be drawing along and follow. Next thing you know, I've got a mark and it's like, oh man, why did I do that? I wish I would have done it. We get grungy fingers, dirty fingers and everything else. Also try to keep it off of the workbench where it's just completely getting filthy, greasy. Not only that, but if you're welding, quite possibly the grinding marks are coming over and poking a bunch of holes in it and burning holes within your paper. Most of you noticed that in the shop by now. And you need to make sure that you look at it, pull your measurements, get it figured out, and then roll the prints up or put them away in a safe place to where they're not going to get grinding marks and grease all over them. Okay? Okay. Do not mark on the drawing. The notations added only by the person in authority. Occasionally you may have an engineer that's done an as-built to it. So an as-built means that quite possibly they changed the design for some reason or the other. Say originally the entire blueprint was good, but they found a flaw within the design of one portion, or the company may have suggested that they wanted like a secondary valve or a secondary check valve in there to make sure for emergency precautions, so to say. Okay, so a lot of times a person can put that in, a person of authority only, use the welder or fabricator, machinist, whatever. Don't do it on your own. If so, get a copy of it and then make an additional print that you have kept separate. Don't put it on the file itself. Occasionally what I've done is I put on the bottom, I put revision, see page so-and-so, as per whoever authorized it. And that way you have the original one, plus you have an as-built copy as well. And it might simply be, in the old days we used to call it red lines. So if somebody would come in with a red pen or a red pencil, they would draw it in showing that it was an altercation to the original design. All right? So the types of lines, border line is a real thick, heavy line. Okay. The object line shows the shape of an object. Visible edge lines may vary in thickness depending on the size. The extension line express the size of the object, extend away from the object, not part of an object. Line medium in thickness, but however it's still a solid line, not unbroken. Okay. Dimension line, a lot of times you will see it with arrows here to there, showing pointing in this direction. Not always. Sometimes you're going to get small prints to where you may not be able to see it. However, if you see a straight up line here and it says 6 inches, we can assume that that still is a dimension line. Okay? Center line, light broken lines made up of long and short dashes. Not part of the drawing. Not always part of the drawing. However, in certain, in a lot of pipe fitting diagrams, I have seen this. Just to clarify, it used to be it was all off the center line. Now they'll do a 3D projection or an isometric view, and they may show all outsides of the fitting depending on wall thickness and so forth, okay? Invisible edge line, nice even pattern broken dashed lines, okay? Phantom line, it's a light broken line make of series, one long and two short dashes used to show alternate locations of a part designed to move through range and motion. We'll explain that a little later on. Cutting plane line indicates our imaginary cut made through an object. Leader line, dimension or note drawn at an angle. The leader also is associated with a welding symbol. Might be showing you this is done with a shielded metal arc welding. Weld, so position and so forth. We'll cover that a little bit more later on, and specifically in chapter 30 as well. Okay? Series of lines that are solid are broken. So if you're going into an engineering spec, you'll probably see more of this than you would in just the everyday shop use. A lot of times they'll just give you what the material is. They may show you a shaded area. However, for the most part, I've always made sure to pay attention to the details within the drawing of what grade of material and type of material it is. I have not went off of just the shaded areas and what they should represent in this manner. Okay, so always don't just go off of this. Make sure you go to the detail within the drawing, look at the material spec, and use that for your reference. So here's a good example. This one you can see it's a rounded object, both of them. This is in a solid one. This is within a pipe or a cylinder. Okay. So let me come back to here real quick. The types of lines. We're on page 975, chapter 29. And I want you to highlight each one of these and understand what the meanings for them are, okay? Whether it is starting with underneath types of lines, page 975, left-hand column about halfway down. In bold print, each one of them, the object lines, the shape of an object is shown on a drawing by unbroken heavy lines. Next bold one, right-hand columns, extension lines, dimension lines. I would highlight them, write them down just for reference to know them. Put them in your notes, something you may refer back to occasionally. You're going to see this and this, and you're going to think, oh, which one was one dash or two dashes? Man, I forget. Sometimes it's self-explanatory, but occasionally you get quite a complex print to where you want to make sure you have the right line and you know what you mean and so forth. Okay, moving on. Page 976. Underneath leaders, break lines, projection lines. Now we're under dimensioning on the left-hand column, bottom page. I'm going to read through it. The U.S. customary and SI metric measurement systems, the two most commonly used systems of measurement throughout the world, are the U.S. customary and is abbreviated U.S., sometimes called the inch-pound system, and the metric system, which is based on the meter, liter, and gram. Pretty important to know those three things. What's the basics for the metric system? It's a meter, liter, and gram. So I would write that down for sure. The base of the metric system is known as the meter, liter, and gram. Metric system is a decimal system expressed in multiples of 10. The base unit is 10, and all other units are 10 times the basic unit. The U.S. system most of us are fairly familiar with. I'm not going to read any more through that. So here's some projection lines. So here's kind of what I wanted to note as well. So here it shows the dimension line on the interior. Now as we can see, this is too short of an area to have arrows on the inside as well, okay? So we quite possibly will have arrows on the outside with the reference dimension internally. It's not out here, it's internally showing that that's 5/16 of an inch, okay? So, same thing here. Now this is 1.5 inches, so this is 1.5 inches overall. 2 1/4 inches overall. So this is a good chance to make sure that you are doing your math correctly as well, okay? So 5/16 and 5/16 you're going to double, okay? So 5/8, very simple way to do this. Real quick, so you have a 5/8 of an inch, and you want to take that fraction, you want to cut it in half. Easiest way is to just double your denominator there, okay? So instead of 5/8, half of 5/8 is 5/16. It's the exact same thing here. You want to double this. You cut this one in half, so 16 becomes 8. You have taken it larger. Good chance to make sure you know what the outside dimension is. You're in good shape, okay? You can see there are several dimension lines here. We have object, object, top, front, and a right side view, okay? So as you can see, these are hidden lines, okay? However, we have 1.5 inches looking down from the top. So at this point, the 1.5 inches correlates to here, so this is 1.5 inches, 7/8 here, 5/16 here, 7/8 in the center. If you notice, it comes the same direction. 1 5/8 is the distance from here to here. 5/16, 5/16. So at this right here, we can tell that the outside surface is solid here and here. So what we have is we have a piece of square tubing, okay? It's actually rectangular tubing, but it is what we call underclassified material grades, square tubing. Dimension-wise, it's 1.5 inches by 2 1/4. Okay? Our hidden lines are showing on the inside, the hollow section. This would be shaded. This is solid piece of material. Okay? We talked about our measurement systems. So, see if it does a dimension. Okay. I'll give you a typical conversion, which it has the conversions on page 977. So if we look here, there's hard conversions done only when required. One measurement, so a 1/2 inch diameter, may not have an equivalent, an even equivalent. It's 12.7 millimeter, bolt is not available. Okay. Now there's certain corporations that have oddball sized numbers as well. So for example, Caterpillar may call it a 12.7, and they may refer to it as a 12.7 millimeter. Same thing as a 1/2 inch bolt, but Caterpillar may reference it as a 12.9 or 12.7, millimeter bolt. So as we can see this, we got 1/2 inch, we want to double it. We're at 25.4. That's one of the easiest, the number right away to put in your head to help convert from inches to millimeters is 1 inch is equivalent to 25.4 millimeters. Okay? The reason I'm writing this down